Bummer. Okay. For those of us just joining us, soup. No other context necessary. Soup. So the first topic we're going to cover today is naive Bayes. And it sort of, and one of the things that I mentioned kind of is it being very similar to KNN in that there's sort of two types of models. We have sort of the one model that sort of learns something about your data and then kind of applies a decision function. And then there's the other models that just take your data as is, and that is the model. So naive Bayes is one of those. Pop quiz, can anyone tell me what the other one is? Yes, KNN. Awesome, Monty. Yeah. So in KNN, right? It's the same thing. KNN, you're right. There is no explicit training testing there. In KNN, your training data is your model explicitly. And so for naive Bayes, it's sort of the exact same idea that whatever you do your training test split, whatever your training data happens to be, that is your model. That's what's used to calculate these probabilities. And so Bayes' theorem obviously is sort of conditional probability. And so it's if you have the probability of A given B is equal to the probability of B given A times probability of A all over probability of B. So in our case, A in this case is the probability of a classification value. So if you're doing a binary classifier, we're going to be looking at sort of two probabilities. The probability that value is 0, the probability that value is 1. And then B in this case is kind of the unique set of sort of the unique instance, I guess, of our feature space. So, if you think about like if you have, let's say, 3 variables, x1, x2, x3, in this case, B is just whatever that unique permutation of x values happens to be. So what the probability is associated with that. Now, so just kind of a couple other things to note here. Because we are comparing, we're doing 2 calculations. We're going to do the probability of a 1 label and a probability of a 0 label. We can effectively, we do effectively cancel out probability of B from our equation. It's just kind of easier to just calculate the numerator because the denominator is essentially the same in both cases. The probability of B is the same in both instances. So all we're looking at really is the top thing. And so that's what you'll see in terms of how we formalize it. We just calculate the numerator. That's sort of one important thing to note. The other thing to note is naive Bayes, sort of part of the naive aspect of naive Bayes is assuming conditional independence. So for our x1, x2, x3, we just completely assume that they're independent. And so thus the joint probability of that particular combination is simply the product of those individual probabilities. So the probability of x1 times the probability of x2 times the probability of x3. So then again, sort of formalizing this. So what we're effectively solving for is the probability of a given label, or the probability of a given label given our particular data instance is equal to the probability of this particular given instance given that label times the probability of that label. And that's really kind of what we're solving for with this. So that's the formalized notion. We're going to go through a very specific example, but any questions on that? Okay, so then let's do golf. So we are going to, so in this case, we're going to do a binary classifier. It's going to be, are you going to play golf or not? So this is kind of a sample data set, and we're provided with 4 features. We're provided with outlook, temperature, humidity, and windy. And so you can see here, here's our classifier, the play golf. So we have some no instances, we have some yes instances, and these are the factors: how windy it is, what the humidity is, the temperature, and I guess the temperature outlook. And these are all, as you can see, sort of categoricals. So, and then we're going to be asked to use our Bayesian classifier to predict whether or not you're going to play golf given, this specific set of conditions. So in this case, we're instancing in outlook equals sunny, temperature equals hot, humidity equals normal, and windy equals false. More water? Oh, yes, please. Thank you. Okay, so any questions on this specific example? So in this case, our label is, will they play golf or not? We have these 4 variables, and we're given the specific instance, and you want to determine whether or not sort of what label we should assign to this case. Okay, so sorry. So there was a question about what allows us to ignore the denominator. So what allows us, so let me actually go forward, for example. The reason we're able to ignore the denominator is fundamentally we're going to calculate 2 things. We're going to do the probability of yes, given, in this case, today's circumstances. So that's whatever our data frame happens to be. And then we're going to solve for the probability of no. So we're going to do 2 calculations. And because we're doing 2 calculations and we're going to do them side by side, and in this case, the denominator will be the same. B in this case is the probability of today, the probability of today's unique set of circumstances. And so because those are the same, we can essentially ignore them because all we're really interested in then is the numerator, because we're looking at the ratio of the numerators. So we can kind of just cancel out the denominator because they're the same in both instances. Does that make sense? So, I mean, ultimately, we just want to see which term is bigger. So because this term is going to be the same. So in this case, it's play golf or not play golf. So this term, the probability of today's circumstances, those will be the same. The only question is this will change. And so the only thing we really need to calculate is the numerator, and then just see which one is higher. And we can assign the label. So here we can kind of look at, so again, here is our particular test set. So we have our x1, x2, x3, x4 terms. We have the specific values associated with it. And let's just call that today. So remember, we're going to look at, so in this case, our B is the probability of today. So our conditional, our Bayes formula for is the probability of a yes label given today. So in this case, we're going to say, remember, these are the independent probabilities. So going back to here. So remember, probability of a yes given today is the probability of today given yes times the probability of a yes. That's fundamentally what we're solving for. And then what we said is, because we assume conditional independence, we're going to assume that the probability of today is simply the product of the probabilities of each individual feature just multiplied together. Thank you. So we have the probability of it being sunny given yes, the probability of hot given yes, the probability of, where are our features? Probability of normal given yes, and the probability of false given yes. And we just multiply those together, and that will give us our probability of B given A. We can just sum up our probability of A, and we'll get our result. So here we have a few sort of, these are just the total data tables for our data frame. Sorry, hold on a second. If you were asked to do this on the exam, and I don't know that you would be, I actually haven't seen the exam. I have no idea scope or anything of that, so I can't really give you any guidance on it. But if you were asked to do it, you might be asked to do something like this. And so where you'd be given these tables, and you would just simply have to tabulate the probabilities associated with them. So in this case, the probability of sunny given yes, so we'd go to this table. So sunny given a yes is 2/9, right? So there's a total of 9 yeses in our data set, and of those, sunny is 2 of them. So it's 2/9. Probability of hot given yes is also 2/9. Humidity, what do we have? I guess, normal, 6/9. And then the last one, wind, is also 6/9. So, and then the probability of yes itself is probability of total yeses divided by the total, which is 9 plus 5, which is 14. So we just multiply all of those together again, and then we get our resulting value. And then we basically run the exact same exercise for no's. So in this case, our denominators would be 5, but sunny would be 3/5. Temperature would be hot, so that would be 2/5. Normal would be 1/5, and then this would also be false would be 2/5. And then here it's 5 divided by 14. We multiply those together. So do you guys see how we get these associated values? Okay, cool. So then so we can stop there. We don't really technically at that point have to do anything more. Oh, yeah, thank you. We don't have to do anything more because obviously probability of yes is sort of an order is clearly much greater than a probability of a no. So we can just stop there and return a yes. If we want to, we can do the add step of just normalizing it, which would be you just take the individual probability divided by the joint probabilities of the two times 100, and that'll give you an associated percentage. So it'll tell you, that if given those set of circumstances, 67% of the time we could anticipate it being a yes, and 33% of the time we would anticipate it being a no. So if we wanted to, we could return that as well. But either way, from a classification standpoint, you simply get your answer there. Now, one, I guess, little nuance here is that, so remember, we spent a lot of time talking about not only calculating our models, but then also the decision functions. And so I should note that with Bayesian classification, you do have the option to layer a decision function on top of it. So right now, we're just kind of doing a very simple metric that says whatever has a higher relative probability is the one that you assign the label to. But we could, just like with logistic classification, just like with any sort of classifier model in which you develop ultimately probabilities for, you could design a decision function to say only assign a yes label if it's above 60% or 70%. So just because in this case we've assigned a 67% to it doesn't mean we have to go with that. We could just, again, if we are super careful about type 1 errors and false positives, we could say, oh, well, I need a greater than 80% certainty in order to run it. So you may just assign that there. So there is that kind of nuance there, but I hope you get kind of a sense for it, for how this works. Again, very basic thing. These probabilities, one thing I'll also note, are, as you can see, are just based entirely on the data that you're given. So you don't make any assumptions about the broader universe of data. You don't make any assumptions about data distribution, skew, bias. You just assume the data that you're given is statistically representative of the universe of data, and you calculate your probabilities based around that. And hence, kind of bringing it full circle, that's why I said, in this case, the data is the model, because you're just using the data to calculate these probabilities. So again, I don't know if you would be asked to do this. I know on the homework you're not asked to do this, but it's possible for the exam you would be. But if you are, hopefully you get kind of a sense on how you would do it. But let me pause there. Any questions? This only works for category. So that's an interesting thing. I'm tempted to say it would only work for categoricals because I don't know how you would get discrete probabilities for numeric, but that's a good question. You may, so you may need to do like a probability distribution for it. I mean, as long as you can generate, theoretically, as long as you can generate a probability, you should be able to. But it's a good question. I'm not sure how it works for continuous variables. But at least I know for sure it works for categoricals, but I don't know how numeric variables would do. Like if you would do yeah, it's kind of hard to do numeric because you're ultimately doing a binary classification, and it's like, unless you kind of bucket it, you'd say, what is the distinct probability that you would get a 32.5? The probability of that is probably infinitesimal for any one particular numeric value, even if overall that feature could be correlated. So yeah, for now, let me not say for certain, but let me just say I'm not clear how a numeric feature would work for Bayesian. But if anybody knows otherwise, please indicate it. But for now, I'm not clear how it would work. I mean, I can guarantee you wouldn't be asked that on an exam. But yeah, it's a really good question. Okay, moving right along. Topic number 2, perceptrons and neural nets. So I don't know how. So in the interest of time, so I have details on perceptrons. I have a kind of a detailed work through for neural nets, but I don't plan on, I'm just going to kind of like hop ahead so you can see these slides. But like, yeah, I even have a whole category about supplemental slides for neural nets, because I actually work through kind of an example of how you would kind of solve for the learning function, kind of like how that works, but it's a lot to work through, and I don't know that you would need it. So so I'm going to go through the perceptron, I'm going to go through the neural net theory, and I'm going to leave those slides there. And unless I sort of get an indication from professor that this might be relevant to the exam, I'm not going to actually go through this. But if I do get some indication that it might be relevant, then we'll circle back. I'm actually going to work through this problem. But for now, I'm just leaving those slides up there for you, but just so you're aware. Okay, perceptrons. So the arch enemy of the Autobots. So I know professor kind of besides. Oh yeah, sorry. Yeah, there's a question through. So again, slides are not uploaded yet. I haven't created the page. I didn't have time. But I think if you scroll, let me just, where's my chat? If you scroll way up here, link is here. I'll just post it on the bottom so you have it again. You should be able to access it there. Okay, so I know sort of professor kind of gave an overview of this, and so I don't know if conceptually you want to kind of run through this. Let me know if you do, but sort of at a very high level, this is modeled after biological neurons, which is, you have for your high school bio, you have on one end of the neurons, you have these dendrites, which are essentially neuron receptors that when they receive kind of interneuronal signaling, it sort of builds up internally, and then at a certain point, once it crosses a certain threshold, the neuron itself will sort of fire along this myelin sheath and will sort of produce outputs there. So, and again, just using this as do I have a thing? So I know the professor kind of talked about the history of this, but it's kind of interesting how like this was how the evolution of like neural nets as a learning model, because this is actually one of the oldest neural nets. As you can see, like as early as 1943, the initial sort of conceptual model was defined. Kind of one of the cool things that were developed in the 50s was just kind of the learning rule and the training rule for that. And we'll go over kind of how a perceptron will sort of learn and how it'll converge on a problem. And then, and sort of like if you study the history of machine learning and everything, like the kind of the sort of plateau that was reached with regards to early stage neural nets and sort of the challenge, particularly with perceptrons, and kind of flatlining of work along there. And it was perceived for a number of years that was kind of a dead end. And then with the development of sort of taking the perceptron model and making it sort of a multi-layered, literally neural net, how that sort of just opened up a whole new facet of classification and has kind of led to the explosion sort of deep learning applications that we have today. So, and again, if we have our little thing, we have these series of inputs here, we have sort of an activation, we have an outputs. So here, our inputs will look very similar to a number of the models that we've had, where if you think about this as a quadratic form, where you have a number of inputs, a number of x factors, and these could be categorical, these could be numeric functions, and you have an associated coefficient. So associated with it. And so you can have a constant, in which case it's just your input's a 1 and there's weights. You can have variables. And again, these can be either categorical or numeric inputs and the weights associated with them. And the way a perceptron works is it kind of just takes all those inputs, it takes a weighted sum. And then at a certain point, we have this sort of nonlinear, essentially step function activation, right? It's either a 0 or a 1. You cross some predetermined threshold, and you sort of determine whether or not this neuron will output accordingly. So that's generally speaking how the model works. Let me see here. Okay, so let me get into it. So again, conceptually, I think a very simple one. You have this quadratic form. It's broken down here. You just kind of take the sum of it. If it crosses a threshold, you output sort of a binary set of outputs. Any questions in terms of kind of like the basics for how a perceptron is modeled? So yeah, so there's a question of like the different activation markers. So you can actually, one of the things that you can change for neural nets is you can change the precise activation function. Like you can set the threshold, you can set which one you use, whether or not you use something like a sigmoid or something else. That is one of the things that you can adjust. So it doesn't necessarily have to be a 0 or 1. So it is worth clarifying that. But usually it is a binary output, but it doesn't necessarily have to be a 0 or 1 binary output. You can choose different things. So, okay. So then let's talk about like our learning model. And at this point, we've kind of played around with different learning models, but so I guess the first question is, what is it when a perceptron is learning? What exactly is it learning? And I think that's kind of important to note this. Now, what can a perceptron theoretically change? So really, you can argue it can change one of two things. We can change our step function. We can change our activation level. We can change what our threshold is, what our output is, right? We can theoretically change that, but that doesn't really give us a whole lot of flexibility in terms of building this model. And it doesn't really allow us to kind of get some more nuance. We can't change the constants because this is our data, right? This is the data that we're fed to give ourselves the model. So really, the thing that a perceptron learns is the weights that it attaches to a model. So, in plain language, right, this is just like with a linear regression and the coefficients associated with it. You're learning what your coefficient is it's saying, how does this particular feature impact your overall result? Is this something that we think is important? Is this something we want to magnify or something we want to not magnify? Is this something that we want to change in a positive directionality or a negative directionality, right? Like, how do we want to kind of modify this? So that's sort of, in essence, what we're learning when a perceptron kind of learns. And so how does it do that? So it uses this model here, and I kind of badly cropped it so you can ignore those things there. But essentially, so this is our weight here. So this is sort of the change in the weight. So is the result of C, which is our learning rate. That's sort of something that we set that's usually preset at a given time. Very similar when we're talking about gradient descent functions, right? Our learning rate is kind of how big a magnitude of a hop we take. We have T minus Z, where T is your Y actual and Z is your Y predicted. So it's your actual minus your predicted, and then times your sort of the value of x. So for each weight, we then multiply it by the value of x. And let's kind of talk through about this, because I think this is kind of like a really cool, really elegant sort of solution. So the first thing to note is that you will only change the weights if your perceptron is an error. If your perceptron was supposed to calculate, let's say, a 1 and it did a 0, or a 0 and it did a 1. So in this case, when they're equal, if it's a 0 minus 0 or 1 minus 1, this term cancels out. And so your overall delta becomes 0. So it'll only change it if you make an error, is kind of the first thing. The other thing that's kind of elegant about this is it controls, by positioning it this way, it controls the directionality of the shift. So because this is your y actual and this is your predicted one, if you, if you think about this as like a false positive, so in other words, I predicted 1 where I should have predicted 0, this would be a 0, this would be a 1, which means my overall term will be negative, which means my delta, the direction I change in, will be negative, which if you think about it is exactly how you want this to do. Because in this case, what had happened was you took your weighted sum and it was above your threshold. So you returned a 1 when you should have returned a 0. So what this is saying is, no, you need to lower your coefficients because in that instance, it should not have produced an activation. Conversely, if you get a false negative, if your actual was a 1 and you predicted a 0, then your term is going to be positive. Then you're going to change the weight positively. So in this case, the weighted sum was not sufficient to activate, but it should have. So in that case, you want a positive delta in your weights. The last thing that I think is really elegant about this is you then multiply it by the x value itself. And the reason that that is so important is because that also kind of changes the magnitude of your W and changes the rate at which it's shifting. Because if you think about this, if you're dealing with, right, and this is, remember when we talk about like scaling your data and making them relatively scale variant or scale invariant. So if you didn't kind of adjust the relative weights to be the magnitude of the coefficients, you would essentially be sort of dramatically changing coefficients of lower valued things, whereas you'd be making almost no impact in highly valued things. So by scaling that, you do correct for the relative magnitude of your parameters. So again, I don't know that this was something. I think there might be some questions about perceptrons in the homework. I don't remember. I looked at it briefly last night, but it would not be unreasonable to be asked to do something like this on the exam. And so, yeah, so again, just the point about this is the idea that you don't want to be adjusting all of your weights equally, because the magnitude of these inputs could vary dramatically. And so it's the idea that like because you're taking the weighted sum, you want to ensure that the relative sort of impact of your weight on the overall magnitude is consistent. Because otherwise, if this is like, let's say this value is 1,000 and all these other ones are like 1, 0, zeros, these are 0, 0, 1s, and you're adjusting your weights by like 1, 0, you'll never it'll be much harder for this model to converge. And so that's the idea of like scaling the relative delta in your weights to correspond with the magnitude of the variables you're dealing with. So, if this one's in the thousands, then your weights should correspondingly shift in the thousands as well. And I will note though, kind of, as you can see, this is another example of where it would be important overall though to scale your data for precisely that reason. Because if you have some parameters that are in the thousands or tens of thousands or hundreds of thousands, they may kind of dramatically distort your overall weighted sum. And that's why it's kind of important to scale your data accordingly. So let's see. So essentially kind of the steps to run a perceptron if you were asked to do this. And again, I forget if you're actually asked to do this on the homework or who knows if it's an exam, but you'll create sort of your perceptron node with n inputs. So typically you'll have, like, you'll be given a model, you'll be given sort of a few data points, and then you'll sort of be given an initialization set of weights. So you're given an initial set of data, initial set of weights, then you just kind of plug them in and you say, okay, well, based on this, I'm predicting 1. And then you look at your actual one. And if it is, then no adjustment. If it isn't, then you adjust all of them accordingly. Now, and let's see, apply perception. So one other thing I'll kind of note with this, you continue to kind of, the way a perceptron will run is you will sort of, you kind of continue to run through this and you update each time. And then at sort of, once you run through your entire data frame, you kind of assess if you can do any better or not. So sometimes you'll converge on a solution that perfectly captures it. And if there is a convergence, right, it actually, one of the things that they did was that was prove that this model would converge if one existed. If it doesn't, typically what happens is you'll set a halting condition. You'll say after a certain number of epochs, if you have not really improved, you just kind of halt with whatever, you know, whatever your the solution is that you've achieved up until that point. So that at a high level is how kind of a single neuronal network works. Now, one other thing I'll note that kind of is very different from, sort of previous, well, not from previous, but from sort of maybe different learning models we've learned and from neural nets, is that we change all of our weights whenever we get something wrong. And we change it, we use the same function. So whenever it's wrong, we apply the same formula to all of the neurons. Now, again, that X term changes the magnitude. That's what changes the magnitude. But we apply, right, every time if we get it wrong, all of these update. Every time we get it right, all of these don't update. So that's, I guess, kind of something important to learn. Now, when we get into neural nets, each one has its own kind of unique formula based on its partial derivative. But for a perceptron, they all follow this learning rate. Okay, so that is perceptrons. Okay, so on to neural nets then. So, you know, as we noted, we have, you know, that's a nice little single neural model, but that doesn't kind of capture a lot of the complexities of computational capabilities. Neural nets are kind of designed to capture sort of those more complex interdependencies. And generally the architecture of a neural net, so if you kind of keep this in mind, we'll kind of walk through all these, but you'll have your set of input layers. You'll have a bunch of kind of hidden layers, and then ultimately you'll have your outputs. So your input layer is just kind of your basic thing. There's no computation done here. You're just passing information to. Your hidden layers are where that sort of intermediate computation is done. That's where all your activation thresholds are. Right? So, you know, different sort of multiple different thresholds. Like for this one, we'll take inputs from, I guess, these three. I guess in this case, they're all fully interconnected, but they don't necessarily have to be. It'll make an activation decision, and then it'll output, and then it gets output to there, and then it'll make a decision and output, and so on and so forth. Your output nodes, that's kind of the resulting thing, right? After you've kind of fed forward your data, you've kind of got this series of sort of cascading reactions, you're going to get your output nodes eventually. That'll sort of give you an ultimate result. And then just like with the thing here, where you have for each sort of input connection, you have an associated, you have the value that's fed in, and you have the associated sort of weight with it. So you're going to kind of do the exact same thing here. With each input, you're going to have the resulting sort of the output of the previous layer, which will be equivalent to your X value. And then you'll have the weight that this layer, that this associated layer will have with it. And then, of course, our activation function, which is much the same. Sorry, Sorry, what is the question? What do you mean by transfer the weights? Where do I say? Oh, yeah, sorry. By transferring the weights, I guess what I'm saying is it transfers the adjustment. So you're not literally carrying, each weight is calculated separately, but it's the, yeah, that wording is a little bit ambiguous. So it's the idea that, like, again, just like our perceptron model, you have your inputs, which are equivalent to your x's, and then you adjust it using weights, and then you feed forward that sort of new output to like the next layer. So you're transferring your weight adjusted output, I guess is a better way of saying that. And then, of course, ultimately, we're going to get into our learning rule, which, as I already kind of noted, is based on sort of the partial derivative, and we'll kind of go into that. So there's kind of the two steps of it. There's the feed forward and the back propagation. So feed forward is pretty much the process with which we've kind of said. You have sort of a series of interconnected functions, and you can do different sort of things here too. So I kind of mentioned that you'll see here, which you may have. So this is kind of an example of a feed forward thing where you'll have sort of a weight and an associated input. You'll have your activation function. I'll give an output. This will sort of, this is a sort of transformation function that will transform your function. That doesn't necessarily have to be a specific activation function, but it might. You take that output, it has an associated weight associated with it that you learn. And again, you then take that output function, you can do it through another kind of transformation, and then you'll arrive at your final result. So that's kind of your feed forward aspect of it. And then there's the back propagation. So based on your output, much like we have kind of a learning network here, where we evaluate, whether or not it worked or didn't, and adjust our weights accordingly. That's where I'm getting a weird beep through my mic. But just like we kind of have that learning, so the back propagation is based on our results. We kind of work backwards through this model, and we kind of adjust the weights along the way based on how the overall error is the result of that. And it's a little bit difficult, as I note here, because these components, like, it's hard to say how this particular input will impact the overall error rate just by eyeballing it. So what you have to do is ultimately you kind of calculate the partial derivative of this particular input with regards to the loss, and that becomes your activation. That becomes your learning model. So again, plain language for back propagation, you're going to take your final loss function. Typically, it'll be, it might be like ROC or some kind of variant, and then you calculate its derivative with regards to the final model output. From this derivative, you then use the chain rule to kind of break out the subcomponents into partial derivatives, and then you kind of work backwards until you reach the specific derivative of the loss function in relation to that specific weight. So once you have that partial derivative, then you can kind of just take this function here. Your new weight is your original weight minus whatever your learning rate happens to be times the partial derivative. So, and again, I don't know if you're going to be asked to do this. You may not. Last year they were asked to do this, and so that's why I kind of have some notes. I have an example here, and I can just kind of show you how that works. But generally speaking, kind of if you're asked to do something like this, you just start with abstraction. So you kind of build, if you will, the model of how that network works, how those partial derivatives are determined. And then you kind of keep a table of those relationships. And then you work backwards until you've kind of fully articulated all the partial derivatives. And then you would take the specific inserted values and you would solve them. So, and again, I have a specific example here. You have your ultimate loss function here, which is your y actual versus your predicted one. And then, oh, sorry. So let me kind of, I'm sorry. Let me articulate what this is example, because I didn't do a good job of doing this. So in this case, what we're looking at here is you have your initial weight and your initial X value. You multiply them together because they're a product of each other. That gives you an intermediate result. You then plug that through your activation function. That will return, whatever your activation function happens to be, a 0 or a 1, that returns that output. You then go to the next layer of your neural network. It takes that input, the associated weight with it, multiplies it together. That gives you your intermediate value. You then put it to the next activation function. That'll input, again, and ultimately an output. And that output, that A2, is ultimately your predicted value. And then your loss function is just your ultimate predicted value in relation to your Y value. So, and again, I don't necessarily want to kind of work through this, but you can kind of see here your overall loss function in terms of weight 1. So let's say, so ultimately, right, if we want to solve for this, you're ultimately the partial derivative of the loss function in terms of weight 1 is just sort of the chain rule for the loss function in terms of A2, which would then be the partial derivative of this A2 output in terms of Z2, this Z2 output in terms of A1, this A1 in terms of Z1, and then ultimately Z1 in terms of weight 1. So, and again, I kind of, in these slides, we kind of go through like some specific examples of how you derive each one of these and how you break them out, how you table them, and then ultimately how you would calculate it. But hopefully you won't need to do that, but it's just kind of important for you to kind of recognize that ultimately you'd want to get to something like this, which is a sort of like a fully articulated how you would adjust weight 1 would be your original weight 1 times, and then these are like, at this point, once you've solved for here, these are all real values that you can just kind of plug in. And you would get your learning rate for that. So it's a lot. Again, I don't think you're going to be asked to do that, but the slides are there just in case. So yeah, so again, so again, there's the question of like the back propagation element of this. So again, it's just the idea that like you have this feed forward thing where you have your initial inputs, it's kind of feeding forward through your neural net. And in this case, so what we're looking at here is we're essentially looking at 2 neurons. And so you start with your thing that feed forward here, you get an eventual prediction, you have your loss, and then the back propagation is just kind of cascading that loss back and adjusting. In this case, we would want to have adjustments to W2 and to W1. And it's just kind of figuring out those relationships in terms of their partial derivatives with regards to the ultimate loss function. So that's a lot. And again, I don't want to necessarily get too in the weeds on that because so far I don't think you're going to be asked to do that. If the professor indicates that that is relevant to the exam, we will definitely like go into the weeds and we'll actually like work through how each of these things are derived, what they equal, how you kind of do this. Again, it's there if you're interested, but I feel like just for the sake of time and frankly your sanity as well, I kind of want to leave it at that high level. But yeah, let me take a pause there and see how y'all doing with that. Okay.
I have a question.
Yes, go ahead.
So, so could you say then that like basically the individual perceptrons are optimized with like the larger picture of like the loss in mind? Like they're not each optimized in isolation. They're optimized with respect to like how the entire neural net, or with respect to the loss of the entire neural net.
Yeah, so I think that's correct. But I think that the distinction between sort of a perceptron model versus this is, so with our little perceptron, it was essentially kind of all of these sort of impacted it in the same manner, and right, because it was just this single degree here. It was just a single input, single thing, right? So it was all kind of in the same manner. And then the only question there was like the magnitude, the relative magnitude based on the degree of the inputs. Here, because you can get these really, really complex networks where different neurons will relate to different, will kind of have different cascading effects in the pattern. And this actually isn't a particularly good example because here every neuron is connected to every other neuron in the layer. But you can very easily imagine a thing where like this particular input just goes to this hidden layer and just goes to this output, whereas this one is connected to all of them, this one is connected to all of them. And so the result is that like the impact that each one has and the associated kind of weights with that is correspondingly different. And that's why we kind of have to go the added step of not treating every mistake uniformly the way we do with the perceptron, but saying we have to look at how each, how, again, looking at this thing, like how did each kind of weight contribute to the overall mistake that we made? And so while we're looking at the overall loss function, what we're trying to tease out is saying like, how did this particular interaction contribute to the overall loss? How did this particular interaction contribute to the overall loss? And then we sort of adjust accordingly. So conceptually, I think that's the difference, and that's why we take the partial derivative loss, is we're really trying to kind of tease out, again, that relationship between a particular weight and its sort of cascading downstream impact on loss. And that's where the chain rule becomes so important. Like we can't, like the impact of, in this case, weight 1 in terms of loss is really kind of this cascading, again, back propagating aspect of the partial derivative of these two terms, right? Which ultimately, if you're looking at these ultimately will cancel out. It's just, you'll end up with this just because you'll be able to cancel these terms, these terms, these terms, these terms, and left with that. But you do need to solve for these intermediate ones in order to eventually arrive at that value.
So in the example of the network that you showed, where everything is fully connected,
yeah,
the neurons still have differences between them if they're all like identical?
They will have differences based on. So I want to say they may have differences based on the relative. Well, let me think about it, because the relative. I was going to say they would have differences based on the upstream weights, but if the upstream weights are the same, then yeah. So I think, sorry, in this case, I do think these would end up being the same, because the only things that would change the partial derivatives would be if the associated kind of upstream partial derivatives were different, but they wouldn't be. You'd have the exact same series of partial derivatives here that would then in turn be the exact same. So yeah, in this case, because we can see they're impacting them in the same manner. They have the same impact on your overall network. So yes, here they would be the same. Okay, so I think that's it for now. Like I said, this will be here, and if we need to return to it and touch on it, I will, I'll get confirmation from the professor on exactly kind of whether or not, like, the different professors are different. Like the professor who taught it last year was big on like students working through a model of this and actually solving it by hand, and that was a huge pain in the butt. I don't know if we're going to go that route, but if we do, like I said, we'll work through, kind of how you get this partial form, and then once you have that partial form, you then try to figure out like what you then solve for, what the like in this case the if your loss function is, I think it's like whatever we're given that particular loss function, so we know that the partial derivative for that is that term. So then we know that term is that. So we just kind of bank that. Whenever we see this, we bank that, and then we kind of you just like work through and solve each term and in terms of real terms. And we just kind of walk through the logic for each of those terms. And then ultimately you rewrite your partial derivatives in terms of, again, these are all real terms. These are all, this is our actual value. The A2 is a real output that you get in your model. Same with that. The weight is already, we already know that. Again, same with A1 is the actual model, and then ultimately your X is your input. And so you get that real value that you can then solve for, and then you just input that into your learning model. So it's the kind of thing where it's tedious, but it's actually not conceptually that difficult to do. But it is tedious as heck. Last thing I wanted to cover today. is principal component analysis. And this is directly relevant to project 3. I think it might be relevant to homework 3. I think I saw something on PCA there, but again, I looked at it like really late last night and I didn't have time to kind of review it, but I think it's there. I know the professor wants to cover it. There's a chance we may talk about exam related stuff. So let's dive in. Man, we're just like, we really loaded up this discussion section. We're doing like PCA and neural nets and God, okay. This was a heavy hitter. I'm sorry, guys. So we have been talking about this a lot. You have heard me I'm kind of like a broken record about dimensionality. And one of the things that I mentioned was that like dimensionality becomes a problem. And remember, we started talking about this way back in the one-hot encoding days. Remember when life was so sweet and simple and all the things we had to worry about was whether or not we one-hot encoded our categories or not. And one of the things that we said at the time was that kind of one of the concerns for one-hot encoding was dimensionality, right? We said like if you have a category for states and you one-hot encode that bad boy, you're going to get 50 discrete features. And like that's not a good thing. Zip codes was another one. We're like, oh, hundreds of, thousands of zip codes. Like, do we really want? Like, we definitely do not want to create that. And we sort of went into that a little bit. Into that, and we sort of went into why. And kerneling, remember when we did like the kerneling example, it sort of kind of helped to I think articulate why that works. But essentially it all deals with the dimensionality of it. And for every feature added, kind of the dimensionality of your data becomes sparser and sparser and sparser. And statistically, the sparser your data becomes, the easier it is to kind of be able to kind of find a hyperplane that will be able to kind of cleanly plane your data. However, and this is exactly, this is the trick we do with kerneling. That's the whole idea. It's like if we then kind of converge that down into sort of lower dimensional space, we produce this just dramatic amounts of overfitting. And so, again, like I have this like GRU thing. It's like this idea that like literally if you just start strapping on like completely irrelevant features into your data frame, like complete statistical chaos, and you just add a bunch of those, your training accuracy will still go up. Your loss function will still converge more easily just by nature of it. And I think I have my notes for this. I think I have, let's see, do I have here? Okay, yeah. So, in a one-dimensional case, if you have, so training, let me see here, what I have here. Okay, so just to put this in perspective, we have training in 10 training instances. This is a one-dimensional thing, so it's a line over 5 interval units. That gives us a density of 2. So our sample interval will be 2 per whatever the unit interval is. The moment we go to a 2D case, so 5 by 5 to 25, now it's 10 divided by 5, or so we go to 0.4 samples per interval. If we take that up to 3 dimensions, 125 units, our sample density becomes 0.08 samples per interval, because then you're doing 10 by 125. And so again, just kind of conceptually, I hope that kind of articulates just like how dramatically expanding the dimensionality of your data kind of results in sparseness. And then when you get down to that level of density, statistically it becomes almost certain at some point that you can kind of get a clean hyperplane. But again, as we've noted, that hyperplane isn't necessarily doing anything meaningful. It's not necessarily producing anything accurate. It's just happening to model all of the chaos in your data in a way that doesn't generalize in any useful manner. So clearly dimensionality is a problem. Also, one other thing to just kind of note with this is that, again, the larger your data frame becomes, and particularly like for this project, we already are getting to like a higher order of magnitude data than you've dealt with previously. So like for project 2, I think you were dealing with 300 discrete instances. With this one, your data set is on the order of magnitude of 8,000. And so, and that's not even a particularly big data set either. But just, to think about like the complexity of the data and everything, like if we sort of become, if we allow not only our rows, but our columns to get overly complicated, that can just make a learning model intractable to calculate. So I don't even know I have this in here, but okay. So I guess the first kind of question is, okay, so seems like we got to do some trimming. So let's just, trim our unnecessary features, right? We kind of already have an intuition for how to do this. Let's just run a linear regression or some equivalent thing. Let's look at our p-values. Let's look at, things that are relevant, and the things that aren't, let's just trim them off, right? I mean, that kind of intuitively, that might be like the easiest way to do this. The problem with sort of trimming is that it's not always kind of neat and clean. And this is where we sort of get into issues of sort of correlations and codependence and collinearities. You don't necessarily know, just because a feature may have like a low p-value, may not sort of seem to be associated, doesn't mean there isn't sort of a hidden kind of feature that's kind of captured as a combination of features, right? It's something that we've kind of also played with. And so, by trimming one, you may be inadvertently kind of destroying that kind of networked relationship between them. And because these aren't statistically independent things, we can't just kind of cleanly cleave one without cleaning the other. So intuitively, what we want to kind of do, what we kind of want to recast is saying, before we actually try to kind of trim these features, let's see if we can't transform our feature space into sort of a statistically set of uncorrelated components. And so intuitively, that's kind of precisely what principal component analysis does. It sort of takes a large list of interconnected variables and then sort of allows you to kind of recast that, and allows you to kind of choose the subset that are sort of most explanatory for that. So, if you can see here kind of how this is sort of a nice visualization for PC. Do I get into? Okay, cool. Yeah. Okay. So I do talk about that. Just like how principal components work. If this is sort of a two-dimensional space that we have right now, it looks at sort of the amount of entropy and in your data set and kind of re-parameterizes in terms of the largest amount of explainable variance in each one. So in this case, right now, currently we have, let's say like this is our XY. This would sort of seek to recast it in terms of this being our sort of our new x-axis and this being our new y-axis, and sort of orienting our data along those eliminations, along those features. So there are, and I should kind of mention that there are two types of reasons why we would use this. The first is it can be very useful in terms of feature elimination. And this is kind of what we've been talking about. It can kind of help to trim your data set, and we'll show you that in action in a moment. But it can also be really, really helpful in terms of feature extraction. Just by kind of combining relationships in data in ways that are meaningful, you can sort of create new principal components that can be explanatory. And a great example of this, and I don't have a good map of this, but if you imagine this right here as being, so using our data that we had for New York, remember in project 1, we had Manhattan Island and we had the map there. So imagine, if you will, just visualize that this is Manhattan Island. And of course, along that north-south axis, that's kind of a really, really like useful sort of indicator. But it doesn't kind of correspond perfectly to latitude and longitude because it's slanted in this way, right? You have, Midtown is here, Central Park is here, upper East and West Side here, you have Harlem, right? You have Lower East, like all that is kind of along this axis here. Whereas a simple north-south thing, it kind of captures it, but not really as effectively. And so one kind of nice, interesting sort of feature extraction that you do is like take the principal component of latitude and longitude, and you can generate this nice sort of clean thing where you can sort of then box it out and say, okay, well, like here's downtown, here's midtown, and so forth, and so on and so forth. But that's kind of an example of sort of how a feature extraction could work in that instance. So how does it do it? So it sort of, what it does is it, without, I guess, kind of going into too much detail here, it sort of finds the associated eigenvectors of a covariant matrix of your, okay, well, I'm gonna, sorry, this is what happens when you try to sort of say complicated things on 3 hours of sleep. So each principal component is the eigenvector that captures the highest variance within your data. So it looks at the covariant matrix of your data, and then the eigenvector kind of maps to the highest relative degree of variance. And so again, if you're just kind of visualizing a data set with sort of these 5 inputs, you would look at the covariant matrix, and then you would sort of cast the eigenvector along sort of the range that sort of has the greatest relative explanatory thing. And so this would be like the first vector, this would be the second one. And then it kind of does this in a progressively diminishing factor. So it'll take, so the first principal component will have the greatest explainable detail. The second one will sort of, and so on and so forth. And you can kind of see that this is sort of a mapping here. So proportion of variance and principal components. So just as an example here. So in this particular data set, if you just take the first principal component, you can capture about 30% of your variance. If you go to 2 principal components, you can capture about 50%, 60, whatever you like, as you're going up and up and up, and eventually it kind of begins to converge. And so somewhere along the lines, you might say, well, I'm good with capturing about 90% of it. And if I just take the first 8 principal components, I can actually capture about 90% of the variance in my data. Let's see. Oh, never mind this. I have to update this slide, but I'll talk about that in a little bit. I'll get to that in a moment. But right. So I think one thing conceptually to understand with the resulting principal components is this is a form of black boxing. And when we get into project 3's description, we're going to kind of get into that a little bit more. But what you're effectively doing once you kind of recast things in terms of their principal components is you kind of eliminate the underlying labels. Like these, this label here was meaningful. This label here was meaningful. The principal components, it's capturing the variance in your data, but in terms of what it actually means, it's a bit of a black box at that point. You can't, at that point, you can't really write, it's not really meaningful to report out, oh, the first principal component explains, 50% of the variance in your data. Like that doesn't actually tell you anything meaningful. It's not like saying like, oh, longitude explains 50% of the variance in your observed data, right? That is explainable. That's something that you can kind of explain. This is incredibly useful from a modeling perspective, but it black boxes your data in terms of your outputs. Much like, I should add, like a neural net is also kind of, you may hear of like a neural net as like a black boxing method. And that's kind of why, because given the sort of the complex interdependencies of it, you can't actually sort of tease out precisely how any one input is impacting the overall model. So this is an incredibly useful, incredibly powerful tool, but and again, the other kind of key thing that it does is by recasting in terms of these relative eigenvectors, these are statistically independent, which means that you can trim this. If I just want to keep that first principal component, I can trim that and not worry about them being sort of correlated and sort of cutting data associated with it. So and again, there's kind of there's a question in the chat about, can you find what proportion of a component comes from which attributes? So it's a good question. I'm not sure if you can sort of how easy it is to do that. I mean, so obviously what you can do and what we do is, when we look at like, if we run like a linear regression model or something, right, we can look at the statistics associated with with features and sort of see the degree to which they correlate to your predictors and the degree to which they're important. And that's kind of a very useful step. And I'm sure there is a mapping of that to principal components, but because obviously they're correlated, but I don't know that there's a sort of an explicit way to do that. Okay, so this slide needs to be updated. I apologize for not doing it. Okay. So yeah, so for project 3, there is going to be an explicit step where we're going to ask you to use PCA specifically to reduce the overall complexity of your data set. And I'll prepare some coding examples for you. Let me see. Yeah, okay. So ignore all of that. In fact, I am just going to ignore all this. Just delete that so you don't have to look at that and get confused. Now I have to remember that. Okay, so let me I guess kind of pause there for PCA and principal components. Does that how are you guys feeling about that conceptually?
I still have my question, like, does PCA eliminate your need for cross terms? Because it's like already kind of like, I don't know. It's like it finds like the most, like the area of most variation. So it's like, I don't know. Somehow I get the sense that it could eliminate the need for cross terms.
Yeah, so I think it does. So the answer to your question is I think it does, because the whole idea of cross terms were that there were these sort of complex interactions in your data that if you were just modeling by the individual terms, you're not necessarily capturing. And I think what principal components are designed to do is because you're sort of modeling the variance of your data, not the relationships between the data, you're effectively capturing that. But you're not, but you're doing it by sort of recasting it just purely in terms of variance. So you effectively sort of eliminated any of the features themselves and any kind of underlying statistical relationships that they might have. And you're saying, let's just look at the variance of my model and let's just kind of plot out the relative, let's just plot out that variance. And let's build a model that again, sort of just is as explicable of the underlying variance as possible. So yes, I think it does effectively eliminate the need for those cross terms precisely because it's looking at something else. So it's looking at so it's kind of by capturing the variance of your data, it's sort of trying to capture those underlying relationships and sort of just recasting them. So it's doing something, it's essentially kind of getting at that same thing. In both cases, you're trying to sort of model the kind of the entropy in your data. But in one, you're doing it with your kind of discrete input values and the associated weights with them. And this is just saying, let's ignore that almost entirely. And let's instead just look purely at sort of the covariance of your data and then just kind of plot out that and sort of capture those vectors.
I had a second question. That's okay.
Go for it. Yeah, absolutely.
So the PCA, it's just like, it is purely dependent on the feature space, right? It doesn't take into account the label.
Exactly.
So
yeah,
then,
that's the whole idea, but it explicitly eliminates the label.
Wait, I mean like what we're trying to predict.
It eliminates. I'm sorry. It eliminates. You're right. Sorry. It eliminates the I guess the specific features. But yeah. There's still the underlying label. Correct.
And it like is completely independent of that underlying label, right?
Yeah. So I think, for instance, if we were looking at like doing a regression model, the underlying label here would be ultimately your Y term or whatever, the thing here. So it's still there, but yeah, the PCA doesn't touch the label. I think if that's your question. All it's doing, it's taking your feature space and it's recasting it in terms of these principal components, in terms of these vectors that most explain the variance that's observed in your feature space.
Well, so the motivation behind my question was that I was wondering, like, the feature that has the most variance is not necessarily the feature that's most correlated with the output label, right? Like you could have a feature that's like, got a really wide variance, really large variance, but then like, say it's a classification problem, your label's just scattered zeros and ones throughout it. It's like almost like random. Then like making a component out of that feature would not be very useful. So how does PCA address that?
So yes and no. Because I think the key thing to note here is that you're right to say that variance doesn't necessarily sort of tie into your underlying label, but that was true even before you did PCA. Right? There are some features that may cause sort of extreme variance in your data, but that may have almost no sort of predictive impact. So we aren't necessarily, by doing PCA, right, it's not like, if you're looking at your principal component, it's not like saying, oh, the first principal component is corresponding directly to the associated label. All you're trying to do here is capture the relative variance. So you're right to say that the actual, and that's why, if you did your PCA, like let's say you could run a linear regression on a principal component analysis. And then the coefficients for that would be to say, okay, what's the relative weight you should assign each principal component, much like you would do with your original features. So you're right to say that features aren't necessarily, variance doesn't necessarily correlate to your label, but that was true even prior to doing PCA. So I think a way of thinking about PCA is just simply saying, I'm going to try to map my variance as efficiently as possible, right? I'm going to try to capture the essence of sort of how this data is rendered as efficiently as possible. And that's sort of what you're trying to do. But yes, you're right to say that variance doesn't necessarily correlate to ultimately to predictability. And that's why you would then, right, I guess another way of saying this, principal component analysis isn't your learning model. It's just a transformation you would do to your data to then plug into your learning model. Your learning model then has to learn about your principal components in order to then ultimately make a prediction.
I see. But then I guess like the problem is there is that if you use PCA for feature selection, and that's like kind of flawed because you'd be doing your feature selection like without taking into consideration the feature's impact on the label.
So you would not do, so I think the important thing to note here is that you would not use PCA for feature selection. That's sort of an important thing to note here. And that's actually one of the things that we note with the project. So sometimes you will, so part of the reason for Project 3 that we actually have you run, we sort of have you first sort of run like a linear regression and then do that is because part of what we want to report out is feature selection. We want you to say like, what are the features that are important? If from a business owner's perspective, what could be important predictors? What might you want to like invest effort in gathering? Because yeah, once you kind of cast this as a PCA, you lose that kind of traceability. So this is, again, it's just like plugging it into a neural net. You can't use a neural net to sort of tell you to do feature selection the way you could with like a linear regression, but you can use it ultimately to sort of optimize your model. And so so PCA kind of serves a similar purpose.
I have a follow-up, but if I'm taking too long, we can move on.
Okay. Well, let me kind of pause there. Does anyone else have any questions? Okay, Moni, the floor is yours, man.
Okay, thank you. I guess I guess I misspoke when I said feature selection. I meant like, because when you do PCA, you drop the least varying components, right?
Correct.
I guess like when you're doing that though, you're doing that like without regard to those components' correlation with the label.
Yes, that's, I guess, technically true. Yes. So the question is, what if you inadvertently drop the component that was most relevant to it?
Yeah, or I guess that I can see like the argument that it would be unlikely given that this is the component that has the least variation. But it's like still, I don't know. I mean, you could drop a component that has like some value, maybe not the most, but has some.
Yeah, so you do, so I will say, and I do have an example worked up. I didn't have time to do it today. I may display it next time. But one of the things that like you can run with this is precisely like I actually have an example worked up with the avocado where like, you know, we end up with like 60 discrete features, and then I run a PCA, and then I sort of take different principal component levels and I sort of run the same learning model, and I see kind of how it performs based on that. So like, and I think with like as little as like 4 principal components, I'm getting a model accuracy of like 90 or 92%. Whereas originally it was like 98%. So, you know, so you're right to say that like, so I think one thing I will note though, is that because, you know, ultimately variance is going to be tied to, your classification, right? I mean, the pattern of your data will be tied to your ultimate sort of classification. So I think it's highly unlikely that a principal component that explains almost no shift in your data is somehow the principal component that is explains, you know, everything. Particularly, I should note, once you've normalized your data, right? Like that's another, I think, intuition with this. If you've scaled your data, then if you haven't scaled your data, then yeah, variance could be entirely based on the relative scale and could have no predictability. If you've scaled it though, it should be highly correlated to your overall to your overall prediction. But you know, again, you won't know until you actually run your learning model just to kind of see how much of the variance you need in order to get an accurate read on it. Okay, how's that feeling, guys? You still with me? All right, so I did want to use a little bit of time that we have left just to kind of go through the final project, because again, that kind of dropped last night. I assume you guys didn't have a chance to look at it yet, but there are a couple things I want to kind of call out for your attention. So this, as I mentioned in lecture yesterday, so this is going to be like a real project. We're partnering with a local LA-based tech startup. We're going to be using their data, and so the company is called Next, and it's a sort of a trucking logistics company, and we've included some materials, and we're going to kind of give you some more briefings on this so you can kind of get more acquainted with it. But in general, kind of one of the things to note is that most sort of long haul shipping is done by sort of smaller players, right? You can think of like on the consumer side, you may think of things like FedEx or UPS or the big kind of shipping companies. But when it comes to doing kind of long haul logistics, most of these are sort of privately owned and operated individuals. And so there's a need for a catalyst between sort of supply and demand, right? Linking truckers with load, saying, hey, we have this load coming in Port of Long Beach. We need to get it to New York. Let's contract a driver out of Santa Clarita to kind of come down and haul it. And that's essentially what they're kind of looking to do, is to kind of build that network. And part of sort of for them, one of the things that they want to better do is to understand their network and ultimately kind of build predictive models around their network. So ultimately their goal is to kind of do capacity planning, like to sort of look at their network of available drivers, kind of anticipate what kind of loads they're willing to take, where they're willing to go, things like that. So they want to kind of do that capacity planning. They're not there yet. And part of what they kind of need to start doing is building a model of their drivers. And our first step of that is to build a binary classifier between high performing drivers and just kind of like everyone else. So that's kind of our goal. So you're going to be given this data set, and your job will be to ultimately to kind of build that model. Now, so very similar in a way to project 2, but there are some differences. And I guess kind of some of the key things to call out for you. So the first is, with this one, you're going to be asked to produce a report along with it. And that's, that kind of communicating your results and your findings are really a sort of a critical part of data science, right? We've spent, I think, a lot of time, like if you think about the sort of the process model for data science, There's everything from like hypothesis, research, formulation, data collection. There's all of that, like that side that precedes what we do. Then there's you actually get your data set, you build your model, you do everything. And then there's everything else here, which is how you report out, how you communicate out what you're doing. So it's, I think, kind of important that we like spend some time actually thinking as somebody who is technical, how you communicate out to people who don't necessarily have your background. So a big part of this project is going to be focusing on that report. And this is going to be something you're going to generate for next. This is something that they're going to be, sent them, they're going to read to it and all that jazz. Just like with the other ones, you're going to be given, you have a specific coding project. And unlike with the other ones, we don't have like a segmented structured Jupyter notebook. At this point, we're going to sort of give you a set of coding requirements, and we're going to kind of run through these. In order to like get full credit for that component, you are expected to kind of run through all these discrete steps as part of your project. Then the final kind of thing about this as well is we're also going to host a contest on Kaggle. And so actually, and the contest is already live. It's a private contest specifically for our class. Here, you will sort of, once you build a model, so we kind of, we talk about like training, testing, validation, right? There's all of that. There's model selection stage. Once you've got that, then in terms of like scoring for your contest, we have a different data set for you. And it's kind of a specific scoring data set. You're going to plug that scoring data set into your pipeline, and you're going to output a series of predictions for it. You are then going to upload those predictions to Kaggle, where they will be compared to the actual labels for that sort of data set, and you're going to generate a score. And that will be, I mean, in order to get like from a grade perspective, you're just going to have to be able to submit and get a score for it. But from a contest perspective, the teams that do very well will get bonus points for it. I don't think we've worked out a precise metric for that, but you will get bonus points. You won't, if your model performs badly, you won't lose points, but it's the kind of thing where like you can only gain, right? And then the top 3 groups will also be invited to present their work directly to next leadership. So that's project 3 in a nutshell. One other kind of important thing here is that we're gonna allow and in fact encourage groups of up to 4 members to do this. And one of the things that I noted here is that there's going to be no scaling for group projects. So like you will be expected to do the same amount of work whether it's 1 person or 4 people in a group. So obviously if you want to do it yourself, you can, but we do kind of highly encourage you guys to work together if at all possible. Let's see. Then, yeah, so oh, by the way, there's a question on how well your model performs on the scoring data. You're not going to know it until you plug it in, but I think there's ways of setting your score private and public, and we have to kind of decide what we're going to make public or not. But like, that's where the scoreboard would come in on Kaggle. Like you can kind of see your performance there when you upload it. But because you're not given the real labels, you're not able to actually do any training on your data. You're just able to see kind of how well it does, I guess is a way of thinking about it. So then that's kind of the general parameters of project 3. And again, this is going to be due the Thursday of week 10. So before that last class, you're going to be able to do that. Several things to note with this that are, I guess, a little bit different from what you've done previously. This time, your labels aren't explicitly given to you. You're going to have to, as part of your exercise here, you're going to have to generate the labels yourselves. And this is very typical. You may, when you're doing data science, you may sit down with a business area manager and they may say like, well, what is a high performing driver? And they might say, like in this case, I might say is drivers who are in the 75th percentile of, these things. Like you may define some rule sets for it. And that's what you're going to be asked to do here. So you have to explicitly generate your labels as part of your effort here. The other thing that we sort of mentioned here is that, so this was kind of our point of PCA. So we do want you to kind of run a basic linear regression, not that we expect it to be particularly good, particularly powerful compared to some of the other things you're going to do. But we want you to kind of generate the associated p-values and figure out kind of the associated features that are most important for your predictive models. This is going to be kind of an important thing to do because, again, when talking to your non-technical leads, it's not great to be able to say, oh yeah, well, you gave us 80 features and we did PCA, and based on that we got a model that did this. You want to be able to say, here are the features that are most important. Here are the things that, like, if you're prioritizing data collection, you want to be able to kind of focus on. And so that's why you're going to do this initial thing. Oh, one other thing that you're going to need to note with this, with your label generation, your labels will, if you've done it correct, they should be unbalanced. And one explicit thing that you're going to need to do to determine this is you're going to need to determine how you want to handle that imbalance. And we've talked about some stuff with like bootstrapping and some other things, but like you're going to have to come up with a strategy for that. We're not going to tell you what to do, but we've covered some ideas in lecture and in discussions and things like that. But like part of your job with this is going to be to figure out what you want to do with that. The next thing I'm going to note here is also for your pipelining. So we're not going to tell you specifically like what fields you want you should retain, which ones you should drop. For the ones that you retain, how are you going to sort of deal with like your categorization strategy? What are you going to do for your imputation strategy? Because you're going to see like there's a lot of null values in this data set. You're going to have to kind of figure out how you want to handle that. And one thing that I'll note is it might not be a bad idea to employ multiple imputation strategies. So, different columns, you may decide to do different things with your data. And it's going to be kind of important to think through how each one does. We do want you to see you do some kind of augmentation thing, but again, it's up to you. All of this is going to be sort of up to you to kind of come up with the recipe, to experiment with it, and then just, critically just document. Explain what you did and why you did it. Like, why was this the approach that you took with this? We are going to ask you this time to do PCA. We're also going to ask you to employ an ensemble learning method. Is one of the things that like the professor covered in class, doing bagging or some other kind of equivalent ensemble learning method to try and get a more optimized model. And then we're going to ask you also specifically to do a neural net. Now, it's up to you kind of how you want to do it, but we're going to ask you to do that. We want to see you cross-validate your training for your model. And then the last thing is like, assuming you've done all of that, we want you to then, if you're happy with the performance you've achieved at that point, great. But we also kind of want you to try and play around with your own stuff and see, like, again, as a team, what's the best that you can accomplish with this? Trying different things, trying, different models and approaches, and just kind of seeing what works for you. But again, to get like a full credit on the coding thing, we want you to explicitly see you do each of these steps. And then we're going to ask you to kind of document it, and then we're going to ask you to download that additional data set and go to like, so here's the actual contest. I think you have to register. Yeah, so this is kind of the contest for this. So we're going to ask you to join. You're going to, let's see, data. Can you see that? Yeah. So there is the training data set, that's your full training data set, but then you also have this score data set, which is, that's going to be the thing that you're going to download. You're going to pipeline it and generate a series of labels. You don't know what the actual labels are. When you're ready to submit, you're going to join the competition and you're going to submit it and you're going to get a grade. And then I think, so just at a thing here, we also kind of provide information about like your metadata. So here in total, you're dealing with about 8,000 rows. And this can just kind of show you like all the different features you're going to be dealing with. And like you will need to decide what's going to be important to you and what isn't. And to that end, like we've provided, so Next has provided some documentation to kind of help you become acquainted with the domain. Fiona, who you will meet on Tuesday, who's like our point of contact for the project, she's going to be sort of helping to brief you. She's also offered to come by some office hours and kind of talk to you guys about this stuff as well. So you're going to get kind of a lot of help here, but the idea is doing well on this ultimately is going to require that you kind of have a little bit of domain insight. By the time you're done with this project, you should kind of have a good sense of like a good intuition of what's important and why. So, and again, you have 3 weeks to do this. It's not technically a huge leap from what you've done in projects 1 and 2. In fact, I mean, you're just employing a few new kind of things, but you've pretty much from a Python perspective done everything, or at least functionally equivalent to everything you would need to do. It's just, this is kind of wrapped in more of a real world, less structured manner. And again, we do encourage you to do this as a team, because if you've got 4 people working on this, this should be pretty easy to hack out. So it will be up to you guys. So there's a question in the chat. I'm going to stop sharing. There's a question in the chat about doing the project individual, working on details as a group. It'll be entirely up to you guys how you want to do that. I mean, frankly, you could literally just like have one person do the Python, one person do the report, one person submit to CAG, right? You could totally divide it up that way, or you could within it, you could like get on GitHub and like share your development repo, and you could have somebody, work on the pipeline. You could have somebody work on the model, like however you'd want to do it. It's entirely up to you. I will note that like each individual is expected to like submit individually, but again, it's entirely up to you how you guys do it.
So you say each individual has to submit individually.
Yeah.
If we work on it as a group, wouldn't it be possible that like all of our submissions are identical?
We would expect it to be identical. It's just,
Okay.
I'll be honest. The reason we're asking for individual submissions is it's easier for us to in terms of grading, to like when it's on Gradescope, it's easier for us to just like assign grades and like keep track of submissions that way if it's just submitted individually. But yeah, I mean, we would literally expect if you're a group to have the exact same report, the exact same output, the exact same score, like it should be the same. So it's not like a homework thing where like, do it together, but write it up separately. No, like this is a group project and we expect you to do group work. So yeah, so there's a question. So Google Colab, I think, is a really, really good option if you want to try to like work on it together. Honestly, GitHub is not terrible. Like I've done GitHub as well for, you kind of have to run the environments locally, but like, if you segment these out, I can be like, hey, I did the pipeline, and then just push that. And then you can kind of pull your updates that way. It works. But yeah, Google Colab is not a bad option for if you want to do collaborative data science. But I would leave that up to you guys in terms of how you want to do that. So yeah, any other questions about this?
Yeah, Lionel, I had a question. It's not related to project 3 specifically, but do you know when project 1 and 2 will be graded?
Yeah, that's a good question. I think project 1, we're just about, hang on, let me check. I'll pull up Gradescope right now and I will see where we're at with this. I think we're about ready to release project 1. Yeah, okay, we're almost done grading project 1, so that's going to be released this weekend.
Cool.
And then I know we're going to try to release projects 2 and homework 2 before the exam. So, but I don't know if there's like a specific date. I don't know if it's like for add drop purposes or like pass, no pass. But if you guys have a specific date, like when you sort of need that input back by, let me know and we can try to do that.
Okay. And actually one question now that I just remembered. You were talking about how we have a CSV that's called, I think it's called scores.
Yeah.
And that was to generate labels. Is that right?
Yeah. So the idea of scores is essentially, so there are actually to generate your own labels, there's going to be 2 features that you're going to use. Those features are missing from that data frame. So it's basically just the data you would use in your model. And so the idea would be you would take that data, you don't know what the actual labels are, you would pipeline it, fit it, you would apply your model to it, and you would use that to generate your set of predicted labels. And then you would output those predicted labels and you would submit those to Kaggle. And basically, it's literally like Kaggle right now has a solution set that's like, for this ID, here's the label, this ID, here's the label. And you would just upload your CSV and just do a point by point, like, and you're graded on accuracy.
Okay.
Yeah.
All right, cool. Thank you.
Yeah, absolutely.
Kind of related to the exam coming up in
Mhm.
2 weeks, do you know if homework solutions for like 1 and 2 will be posted?
Yes, homeworks, I can tell you right now, homework and project solutions will be posted. I know there've been a lot of requests of that. So yes, you will get all of those released.
Okay, cool. Thank you.
Yeah, absolutely. Okay, I will stop recording.